Hello, everyone. Apologies for some of the technical difficulties today. Bit of a theme, but that's okay. This is the emerging world of video conferencing we live in over the last year. So, without further ado, I have the great privilege of welcoming Charles to us today. Charles is the co-founder of a secret fintech company that is yet to be announced. So I will be following his LinkedIn profile and using to see when that announcement comes. But Charles is an adjunct professor of computer science at the University of California. He was previously a tenured full professor, and up until 2020, he was managing director of the global head of machine learning at Goldman Sachs in New York. He was one of the first Amazon fellows, leading a team of over 30 scientists and engineers in Seattle, and was doing research and development in machine learning for both e-commerce and cloud computing. He's earned his doctorate at Cornell University, his undergraduate at Cambridge, and his students have gone on to faculty positions at universities including Columbia and Stanford, leading roles in industries that include managing the largest app store in the world. So all to say, we have a very, very impressive CV and tenure and experience that we're going to be learning from today. Charles, in a moment, I'm going to hand it over to you. For everyone on the call, if you have any questions or comments, please put them into the chat and we will collect them for Charles at the end. But without further ado, and because I want to get to him speaking, Charles, over to you. Thank you so much for what you're going to teach to us about machine learning and finance and the lessons we've learned. Over to you, sir. Thank you so much.
Well, thank you, Stuart, and I'd like to thank the organizers of the Toronto Machine Learning Summit for the invitation to speak. This is going to be mainly based on lessons that I learned in the 2.5 years that I was working at Goldman Sachs before leaving, and now, like Stuart said, I'm involved with a startup, but we're currently working on developing our product, so I won't say more about that. Let me try to share my screen so you can see my slides. Great. I hope everyone can see my slides. And I hope everyone can hear me. Actually, I can't tell whether this is working. Well, I'll have to assume that this is working, and I have about 25 minutes to speak, and then we'll have a few minutes for questions. So, like I said,
yes, we can see, we can hear you. Everything's great. Please continue.
Great. Thank you. Yeah. I'm talking about machine learning and finance. I'll talk about artificial intelligence also. And this is based on experience at Goldman Sachs, also at Amazon, and then, of course, all the conversations I've had with people in the industry, people in academia. I think a lot of people at this Toronto event are probably new to machine learning, new to artificial intelligence, and you may have asked yourself the question, so really what is new and what is old? Because artificial intelligence, as the name for a research area, has been around for a long time. The field was really founded in 1956, so that was about 10 years after the first real electronic computers. And John McCarthy was a researcher at the time. Later, he became a professor at Stanford University, and he was one of the founders of the field. And I was fortunate enough to have John as my advisor briefly when I was a student at Stanford. This picture, which I just found relatively recently, I think it's from 1967, and I'm using this picture of John to illustrate how, in fact, a lot is not new. So this picture is obviously staged, and it's obviously supposed to make you think of big data with all the tape drives in the background. It's obviously supposed to make you think of very big, powerful computers with all the other hardware visible. It's also supposed to make you think that playing games, this particular chess, is a pinnacle of human intelligence, and that is what artificial intelligence is about. Well, I think we know nowadays that being able to beat world champions at games is not sufficient to have general intelligence. And of course, we talk a lot about big data, and we talk a lot about the massive teraflops of compute power we have available, but those themes have not changed in 50 years. So why is there so much excitement about machine learning nowadays? And the answer is pretty clear. It's because we now have something called deep learning. And deep learning has allowed AI systems to solve problems that they just couldn't solve before. So just as an example, on the left here, here's a photograph and here's a question. And this is a question that a human child could answer. You certainly don't have to be a grown-up to be able to answer this question. How many leftover donuts is the red bicycle holding? Well, you can see the red bicycle, you can see a box of donuts, and you can see 3 donuts. So the answer is 3. And this is actually a training example for machine learning systems, and that's why the answer is provided. But then after training, the neural network can answer similar questions about similar photographs and without being given the answer in advance. And solving this type of problem was impossible 10 years ago, and it's only deep learning which has enabled it. So clearly, deep learning has been a mini scientific revolution, and many of you in the audience probably are familiar with the work of Thomas Kuhn, and it's a very influential theory of how science progresses, that most of the time there's what's called normal science, incremental research, and then occasionally there's a paradigm shift. Scientists really change their whole way of thinking about something, and that unleashes a new wave of progress. And deep learning has been a new wave of progress in artificial intelligence. And the progress has been especially notable in computer vision and in the combination of natural language and computer vision, as in this example on the left. Now, there are many applications in business for computer vision and for natural language processing, but there are even more applications that don't involve those fields. It turns out that deep learning also gives us higher accuracy in many other fields, such as forecasting. And that's something that I'll talk about on the next slide. But first, let me review what is deep learning. So deep learning is the current generation of neural networks. Neural networks are inspired loosely by neuroscience, so by the human brain, by the animal brain, and even by nervous systems in animals that are not vertebrates. Neural networks were invented in the 1950s with something called the perceptron, right at the beginning of artificial intelligence. But then there was incremental research on neural networks, and the field really slowed down. There was a mini revolution in neural networks in the 1980s caused by the discovery of the backpropagation algorithm. There was a lot of excitement about neural networks at the end of the 1980s and the early 1990s. And then again, the field slowed down. There was something called the AI winter because it was impossible to get neural networks to solve more than a limited range of tasks. And then deep learning is the third Kuhnian revolution in neural networks, which started in the 2010s. And if I look at the research nowadays, it seems pretty clear that we're again in the realm of normal science where there's incremental improvements, but the radical paradigm shifts happened a few years ago in deep learning. So current deep learning exploits modern computational power, and it is applicable to almost all the same types of data that humans are capable of absorbing. So deep learning works well on text data, on image data, on video data. And in business, people have used statistical methods for many decades, but the traditional statistical methods are too simple for the massive data that we have nowadays, and in particular for the type of perceptual data that we have nowadays. And so that's another reason why deep learning has caused so much excitement in business for quite a few years now. The picture on the right here is an illustration of how a deep neural network works. So the input here is an image. In this case, it's black and white, and it's only 512 by 512 pixels. And then each gray box, you can think of it being very simple mathematical calculations, really just additions and multiplications, and then a nonlinear operation, sometimes called squashing. But these very simple operations are controlled by parameters which change what the operations do. And there's millions of parameters in the whole system, which is called a network. And the training process adjusts these parameters so that the simple operations end up producing the desired output. And you can see on the far right here, the output is 5 nodes. So the output is actually just 5 numbers. And so those 5 numbers, for example, could be how many cows are in the picture, how many tractors in the picture. And you can see just by looking at the output that although it's very impressive that a neural network can do something like count the number of cows in a picture, it's still going to be very limited because it can't output anything except those 5 numbers. So if you asked a totally different question, like for example, what country do you think this farm is in? The neural network is completely incapable of answering that question because it can't even represent the answer. The answer to that question is not any of these 5 output nodes. This is an example of what we can do with deep learning that we can't do with traditional statistical methods. And this comes from when I was working at Amazon a few years ago. So Amazon has millions, actually tens of millions of products in stock, and needs to reorder these products from the manufacturers or the suppliers. And so Amazon needs to predict the demand for the products. And the demand for products can really be quite unpredictable. Different products have very different seasonality patterns. Some don't have seasonality patterns at all. So at the top left here, so this is 4 different products at the top left. And the product in the top left, that's a product which has a simple seasonality pattern with a big peak in demand before the end of the year. So here, the training data, the historical experience, started in 2015, included all of 2016. Sorry, started in 2014, included all of 2015, and then included the beginning of 2016. And the vertical blue bar shows where the forecasting is beginning. And the blue shaded region is the forecast with I think a 90% estimated probability that the true demand will be within the blue shaded region. And the blue line that's inside the blue shaded region is the central estimate of the most likely level of demand. And you can see that although the actual demand in late 2016 was much higher than the forecasted demand, it was still within the blue shaded region. So we count that as a forecast that was correct. Then if you look at the other 3 boxes, it's similar that you have the historical demand, and then you have the forecast of blue shaded region. And then this is data that we use to evaluate the forecasting method. And so we know the actual demand, the black line, which is pretty much always within the blue shaded region. Now, if you look in the bottom left, this is really interesting because this is a product for which we had very little training data. This product only came into inventory in the middle of 2016. And then we're imagining that we need to make a forecast for it after just a very few weeks of knowledge. So you might think, how can we possibly forecast a year into the future when we only have a few weeks of data? Well, the answer is that we also have other information about the product. We actually have photos of it, and we have text describing it. And so in particular, using the text, we can identify what sort of product it is, and then we can use information from similar products to create the forecast. And that's actually what's going on here. The picture on the bottom right is a sketch of the neural network that we use for these forecasts. And it's an encoder-decoder architecture. So it's similar to the architecture that people use for natural language processing. It actually uses something called LSTMs, long short-term memory machines. Nowadays, this is research from 2017, we might be using transformer architecture nowadays and quite likely get even higher accuracy. But the important point is this is some problem that we can solve with deep learning, and it combines traditional data that statistical methods can use, like time series, but it combines that with, in particular, natural language data, and only deep learning methods can combine those multiple types of data. There's a lot that we can still not do using deep learning methods, and it's really not the case that true artificial intelligence is on the horizon. And the way that I think about what AI methods cannot achieve is that they're not capable of what I call deep understanding. So we can have an operational definition of understanding as the ability to answer questions. And then if you think of a human answering questions, they have shallow understanding if they can answer a limited range of questions, and those questions are similar to each other. Just think of a child that can solve simple arithmetic problems but all the problems are similar to each other, and there's a limited range of these arithmetic problems. Deep understanding is the ability to answer questions using broad context and using broad knowledge, the ability to answer questions, different answers from different points of view to the same question, and so on. And I think it's really interesting that the word intelligence in English has a Latin root, which means to choose between. So in some sense, we're coming full circle here. So intelligence is understanding. Understanding means selecting the right answer. Current deep learning systems have a remarkable ability to answer questions, but they still don't have deep understanding. They can't really use broad context and broad knowledge. And I'll give a couple of examples of this. So look again at this picture of the donuts in a box on top of the bicycle. I actually first used this example in a talk when I was giving a presentation to the Amazon board of directors, because machine learning is very important to Amazon, but most of the board of directors didn't have much familiarity with it. And after I put up this example, actually, Jeff Bezos put his hand up and he said, oh, the answer is not 3, the answer is 3.5. And so that makes you look again at the picture, and indeed, yes, you can see there's a fragment of a donut in the lower right of the box. So is the answer really 3? Maybe the answer is 3.5. Or if you just look at the picture, what can you actually see in the picture? You can see 3 whole donuts and you can see 2 pieces. But how do we know that the 2 pieces are connected together to form a half a donut? Now, I would claim that this is a question where the same question has different answers depending on point of view and depending on what the reason is for asking the question. So if the reason for asking the question is how many people can you feed, then the answer is 3, because nobody wants to eat somebody else's half-eaten donut. And if the answer is just how many pieces are in the box, then the answer would be 3 whole donuts and half a donut. And the reason we know it's half a donut is that if it was 2 separate pieces, then gravity would make those pieces fall down and we wouldn't even be able to see them. So deep understanding, which humans have instinctively of a photograph like this, is something that neural networks still don't have. And deep understanding combines language and vision, but also knowledge and experience. And in this example, deep understanding involves knowledge about gravity, knowledge about social conventions, like giving something to eat to other people, and reasoning about occlusion, about one object hiding another in a picture. So this is an example of what current AI systems cannot achieve. You might wonder, is deep understanding really needed? Maybe for most of our applications, we can be more shallow. And the answer to that question is that there are many applications where we can get most of the way there using shallow understanding, but to really have a successful autonomous system, we do need deep understanding. And this photo is an example of that. So here's a man in the middle of the road and there's a car approaching. So if this car was an autonomous vehicle, then the computer vision system would see the human and slow the car down. And that's a reasonable behavior. But a human driver knows a lot more about what's going on. The human driver knows why this person is in the road, and the human driver knows that this person is actually communicating. The person is using language. The person has his right hand up and his flat forward towards the car. That's a message. That's a symbol. That's communication. And so to be fully self-driving, a car needs to understand symbolic human gestures. And a human looking at this picture can immediately see why the man is doing what he's doing. He's trying to protect the duck with the ducklings. That's using broad knowledge and experience, which artificial intelligence methods are not capable of currently. The level of shallow understanding is quite pervasive, and deep understanding is really difficult to achieve. So face recognition, systems remain brittle. So brittle is the word that people use in the research community to refer to a system that fails in dangerous ways or fails in severe ways when it's outside of its narrow domain of competence. Probably most of you have seen the examples of the adversarial examples that can completely fool systems for street sign recognition. And even without adversarial examples, it's easy to find the limits of current systems. So this is something that I've been tracking with Alexa for many years now. So you can ask the question, this is from today actually, because it changes from time to time. So today I asked Alexa, where is Mount Everest? And I got the correct answer. Mount Everest is located, and it told me where Mount Everest is located. But then I asked a very simple follow-up question, how high is it? And the answer from Alexa was, right now it's 60 degrees Fahrenheit. So somehow Alexa thought, how high is it, that I was asking about the temperature outdoors in New York today. And that's obviously a lack of deep understanding. Natural language experts actually call this issue anaphora. So the difficult part of the question, how high is it, is the pronoun it. So what does that refer to? And for a human, it's obvious that refers back to Mount Everest, but it's quite difficult to build the AI systems that can recognize what a pronoun refers back to. And the lack of deep understanding also shows up in needing excessive quantities of training examples. So in the Boston area, the word wicked is sometimes used to mean very. So just like a phrase would be like, it's wicked cold outside. And if you're not from the Boston area and you didn't know that that's what wicked means in this context, you probably only need to hear somebody using this word with this meaning once, and then you'll figure out what it means, and then you'll be able to use the idiom yourself if you want to. But a machine learning system would need a lot more than just one or a very few examples to figure out this additional meaning of the word wicked. It is still possible to build very successful and useful applications even without deep understanding. And 98.6 is a very successful startup company that's an example of this. So the question that they were asking is, how can we make healthcare visits more convenient for patients and more efficient for doctors? And the basic idea they came up with is an app, and the patient describes his or her symptoms in free text. And then the app uses machine learning to select follow-up questions, and the patient answers the follow-up questions. And then the physician reads what the patient wrote, including reads the questions and reads the answers from the patient. And then the physician can ask for more information as needed. But the initial description from the patient and the answers to follow-up questions provide a lot of information very efficiently for the patient, very efficiently for the physician. And so it ends up that the visit of the patient to talk to the physician can be much shorter, but still with an equal medical quality. And the company has done a lot of careful evaluation, and this technique can reduce the average length of a visit from about 25 minutes to 9 minutes, and patient satisfaction is the same or higher. Physician satisfaction is the same or higher. So this is a major improvement in productivity in medicine. And the key here is that only the physician needs deep understanding. The machine learning uses the free text from the patient to choose follow-up questions. And usually the follow-up questions are sensible and relevant, and the answers from the patient are useful. But if, for example, if for some reason the machine learning fails and asks the wrong follow-up questions, that's not a disaster, because the human is still in the loop, and then the human can ask the right questions. So this is really, I think, a great example of human-machine collaboration and using machine learning where it's valuable and designing an application so that deep understanding is not needed. I have a few minutes left. Let me talk about finance and what is different about machine learning. So finance is different from other areas of business. The quantitative methods have been very central for many decades. So why are people in finance excited about machine learning? Isn't machine learning continuous with other quantitative methods? I think here the answer is that machine learning is fundamentally empirical, while most of the traditional quantitative methods in finance are deductive. And the classic example would be Black-Scholes for option pricing. So Black-Scholes is based on some beautiful mathematical theory, which is based on some assumptions about rational behavior. So Black-Scholes gives the unique rational price for an option given some assumptions. But then if we look at the data, Black-Scholes prices are only approximately valid. They're not exactly valid. And the difference between actual prices and the theoretical prices according to Black-Scholes, really that's empirical. That's the outcome of supply and demand behavior in the market, and that supply and demand behavior is something that we can study using machine learning. The figure on the right here is an implied volatility surface, and if the Black-Scholes equation was a perfect fit to the data, then this would be a flat surface. But since it's not flat, then we know that there's something more to option pricing than Black-Scholes, and that something more is something that can be captured by machine learning because it's an empirical phenomenon rather than a deductive phenomenon. I think I only have a few minutes left, so I'm not going to be able to cover all my slides. What is the same about machine learning in finance? Well, management of model risk is not fundamentally different. Whether it's a machine learning model or a deductive model, it's only approximately correct, and it can fail badly when something in the environment changes. So we need very similar human oversight for machine learning models and for traditional models. I think it's also very important, and this applies outside finance also, to understand the true business process. So I'm sure that those of you who've worked in banks or in lending, you've worked on modeling probability of default and then loss given default. And it's certainly very important to model probability of default, loss given default. But if we look at the real business process, then it's more complicated than that. It happens very often that when a bank has made a loan and the borrower is in difficulty and the loan is heading towards default, then in fact, the loan doesn't default, it's restructured, and it's never recorded as a default. But when a loan is restructured because the borrower is having difficulty, then typically it's restructured on terms that are more favorable to the borrower, and so that's a loss for the bank, a loss for the lender compared to what was expected when the loan was originally made. So if we only recorded defaults and don't record restructurings, then we're going to be missing a lot of information about negative outcomes for loans, and then our machine learning models are going to be over-optimistic for the future outcome of loans that we might be making nowadays. And this is just an article from the New York Times from back in 1990, so more than 30 years ago, about a famous borrower having big loans from banks, and those loans didn't go into default, but they were restructured, and the restructuring was a big economic cost for the lenders. I think I need to stop here and have a few minutes for questions, so I'll just go to that slide.
Wow, thank you so much, Charles. That was wonderful. We actually have one question from Felix, which I'll do in a moment. But is it fair to say that algorithms exploiting short-term inefficiencies in the market are examples of shallow understanding, while traditional long-horizon valuations of assets is an example of deep understanding? Do you see the proliferation of algorithmic trading based on shallow understanding as a potential danger for market stability?
I think that's a very insightful question, because I think the answer is essentially yes. Machine learning algorithms are pattern matching algorithms, and if there's a pattern in financial markets which gives some predictability to the prices, and you have an algorithm that can find that pattern, then you can exploit the predictions from that algorithm, and you can be profitable trading on those predictions, but you're going to be trading away that profitability, trading away those patterns, and other people are going to discover them also. And so that particular pattern is going to become weaker, eventually disappear. And if the pattern disappears abruptly, maybe because there's been some large change in the external environment, then algorithms that are trying to exploit that pattern may suddenly lose a lot of money. And yeah, that can be a risk for stability, especially if many participants have detected the same short-term pattern that they're exploiting. And then, humans who are thinking at a meta level and thinking that there's crowding in the trades, and then using their intelligence to act on the observation that there's crowding, that would be an example of deep understanding. Now, as soon as we define something quantitatively, if we have a quantitative definition of crowding, then applying that quantitative definition and making it available to a machine learning algorithm, that eventually converts it into something which is relatively superficial, and then there'll be an opportunity for deeper understanding at a human level about what are the deficiencies, say, of this narrow, relatively shallow definition of crowding.
Wonderful. Thank you, Charles. We are actually over time, but we had some technical difficulties starting. I want to thank you so much for your involvement today. I'm looking forward to catching up personally on LinkedIn and hearing about your endeavors into the entrepreneurial world. For all those on the call, Charles can be found on LinkedIn. We will look at sharing whatever we are able to after this event. Please join us back in the main expo area for a sort of looking at all our participants and our sponsors and some awards. And Charles, I'll say thank you so much again. That was really, really insightful, and looking forward to hearing more of your adventures in the world of finance and machine learning. Have a wonderful day, everyone. Thank you.
Well, thank you.